Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who are nominated to speak by their senior colleagues. Today we have Ishika Ghosh, who is a graduate student at Michigan State University. Ishika will be speaking on Towards an Optimal Bound for the Interleaving Distance on Mapper-Graphs. Take it away, Ishika.
Thank you so much for this opportunity. I'm glad to be here. So today I'll talk about a project I've been working on for past year with my supervisor and collaborators. So let's get started. So the main motivation behind looking at this project is that I work in TDA, topological data analysis, and I particularly like the graph-based signatures that show up in TDA. And apart from that, graphical data where there is a real valued function attached to it show up in a lot of different domains of research. For example, if we have brain scan data using fMRI, we can have thresholds as the function value, or we can have transport networks where each vertex will have some degree of importance, and that would be the function value on the node, or we can have social media data. So since there is so much availability of data of this kind, we want to compare them and cluster them for use them in machine learning pipelines. To do that, we need a meaningful and computable notion of distance, but as it often shows up, that these distances are pretty expensive to compute. To narrow down to the project I'm going to talk about, so I work on a graph-based topological signature called mapper graph. Uh, Given, say, a high dimensional data, for example, if you look at the picture on the top right, we have a point cloud data, and if we have a real valued function on that data, where here it's like the y-axis projection, and if we have some overlapping cover of that range, if we look at the each corresponding cover element and cluster these points, uh, we can construct the vertex with each cluster. So mapper kind of captures the connected component information with respect to this cover. So each cluster will give me a vertex point in my mapper graph, and we can join these vertices using the points that's available in the overlap. So my goal is to, given these kind of data sets, mapper graphs, I want to compare them, and to do that I use one particular type of distance that show up quite a lot in TDA, topological data analysis, called interleaving distance. But as it is the case with many other scenarios in TDA, computation of interleaving distance is NP hard, so we really don't want to sit down and compute that. So the idea is that we won't directly compute the interleaving distance between mappers. What we will do is we will use a loss function that will upper bound this interleaving distance and perhaps get better and better loss values to get a better bound. So to kind of summarize the whole talk, what we want to do is we want to make mapper graphs machine learning friendly by optimizing a loss that bounds the interleaving distance. So if you look at like the picture at the bottom, we have two mapper graphs and we essentially want to compute the interleaving distance, but we cannot. So we are trying to upper bound it with a loss which is computed between some particular type of maps called assignments. And note that I haven't told you what assignments are. We will come to that later. Okay, to lay the groundwork, what we first do is we express these mapper graphs as co-sheaves, where if we have the data set, the topological space, for example here the point cloud, and a real valued function, we also start with overlapping cover on R. What mapper essentially does is it preserves the connected component information of the inverse image of these cover elements. And we can essentially discretize this mapper graph using the grid structure on R. And we represent this function that we have start with as co-sheaf, where it goes from the category of open sets over these cover elements to the category of sets, and the information we store is the connected component information that I have with mappers. And what I want to do is, if you give me two mapper graphs in this nice co-sheaf form, I want to compare them using the interleaving distance. Uh, Before we talk about what is interleaving distance, we have to talk about what is a thickening. So, for an interval, an n thickening is, if you look at one interval, we just look at n times bigger interval, like on both sides. We essentially look bigger and at bigger and bigger intervals. So it's a functor, and you can compose it with the mapper graph, the mapper functor that I have. And when I say a thickened mapper, what I mean is that we apply this functor on bigger intervals. And if you don't want to look at the category theory line, you can look at graphs. What thickening does is, on the right we can see, given a mapper graphs with say a loop inside, progressive thickening will slowly like make the loop inside smaller. It kind of zips the top and the bottom. So an n interleaving in this context is a pair of natural transformation that takes a functor, a mapper f, to the thickened version of mapper g, and vice versa. And it must satisfy certain diagram commutativity. So these are the two diagrams we want to focus on. We want to look at the mapper f on an open set in functor f, and then we look at the thickened version in mapper g, and then go back to the twice thickened version in mapper f. And also we have this inclusion map up here, and we see that if this diagram commutes, and the other side of it. So the smallest n for which these diagrams commute for all open sets in my domain, then that is the interleaving distance. And since there are a lot of open sets in my space, the computation is NP hard. So we cannot compute interleaving. What we try to do is we kind of try to go around it. We define a natural transformation like maps, which are interleavings, but we define assignments. These are not technically natural transformation because they do not promise the commutativity, and we try to work on those. For this assignment to be a valid interleaving, we need to have these four diagrams commuting. The top two that comes automatically from the interleaving, for a valid interleaving, and the bottom two make sure that this is a valid natural transformation. So given fixing an n, and if we have these assignments, phi and psi, we want to see that, okay, if this diagram does not commute at this level, how much do we have to thicken the thickening parameter k so that this diagram commutes? And this quality measure is encapsulated in the diagram losses, and the loss function essentially measures how far from these diagrams are from commuting. So this loss would be the maximum thickening value where every single type of diagram will commute. And the good news is that we don't have to compute this loss on every open set. We can do it only on the basis of our topology. So we have this theorem from my collaborators. They proved it that for an n assignment, and if we have these two maps, then the interleaving distance is upper bounded by the n that I've chosen and the loss between these two between the assignment maps. And you probably remember this was there in the summary slide as well. Okay, now I have I can compute the loss, which is great, but I don't want to stop right there. I want to get better and better loss. So we want to deploy some optimization strategy there. So do that first, what we do is we express these mappers, which are now in Cauchy forms, as graphs, which would be the collection of vertices and edges. And we use the grid structure on R to generate vertex at each grid point and connect the edges. Also, we every vertex in my mapper graph are come with some height information that is generated with the mapper. And in this case, the assignment, the map between these mappers, will become basically vertex and edge maps. And when I say a diagram commutes, what I mean is that my images should end up in the same connected component. To emphasize on the last point, what do I mean by diagram commuting? Imagine you have this particular kind of parallelogram diagram which checks if I have, say, I don't know if you can see my cursor. If I have this edge on my right and there is a corresponding upper vertex to it, and I see the image of these two using the vertex and edge maps, and with the thickening 1, I see that these two are not in the same concrete component in this slice. However, if we look at a bigger slice, a more thickened portion, these two end up in the same concrete component, and then we say that, okay, this diagram commutes. Um, so once we have expressed our mappers as graphs, then we want to express these maps, the assignments that I'm talking about, as matrices. To do so, first I order each vertex and edges by some increasing function value that I already assign with my mapper. So for edges, for vertices, we there is a function value already sitting there, and for edges we take the lower vertex function value for the value of this edge, and we can construct matrices with this ordering. And since by the construction of this maps, we can only map a vertex and edge to its corresponding height, these matrices will have a block diagonal structure, which is pretty useful in computation. Uh, to give you an example, let's look at one particular type of matrix that I work with. These are the assignment matrix where I store these maps, and I place 1 when there is a mapping between two vertices and 0 otherwise. And for this to be a valid map between my mappers, there should be only 1 in each column. And essentially these assignment matrices are the variables of my problem, and to have the lower loss, what I want is a better assignment, and which will give me a better upper bound in result. So what I do is I express these matrix multiplication, these loss computations which are coming from the diagrams as matrix multiplication, and each in like inclusion and boundary, each relation is expressed as matrices, and we can then express this diagram as like a difference between four matrices and their like multiplication of two matrices and their difference. And in this setup, the computation of loss boils down to finding the largest element of this big matrix that I'm computing. And if you notice, there were four type of diagrams that I was talking about, and each diagram can be expressed as some sort of matrix, and we try to find the loss by finding the max element of these matrices. And note that the orange matrices are the ones, the assignment matrix, and these are essentially are the variables, and these are the ones I'm trying to make better. To optimize, I use a particular kind of optimization strategy called integer linear programming, where my goal here is to optimize minimize the loss, which is subjected to these the whole bunch of constraints that's coming from this table. And this is integer linear programming because for my mappers, each vertex that I have has integer function value. So just linear programming is not cutting it. And there are some non-linearity, especially in like triangle diagrams, as you see here. So this is no longer linear, but we can introduce more variables and linearize it. So I can solve these problems using a Python package called Pulp, and we can get some sort of optimized upper bound of the interleaving distance. To check the effectiveness of my method, I also experiment on some small mappers where I can hand compute the interleaving distance and see how far I am from the interleaving. So I start with a line mapper where every grid point has like one vertex at every height, and a torus mapper which would have a big loop inside. And I can vary the height of this loop and see compute the interleaving between these two. And I know that the interleaving distance between these two types of mapper would be the ceiling over h over 4, where h is the height of this loop of my torus mapper. And I can see that for these sort of mappers, my upper bound actually reaches the interleaving distance. If you look at the picture on the right, the gray dotted line is what the interleaving distance should be, and this orange line is what is the upper bound, and this is the loss, so n plus loss. And I see that even for n equal to 1, when I compute optimize my loss, the interleaving distance is actually equal to the upper bound. That is great. I also run some small experiments with image data sets. So I take some five categories of images from the MPEG-7 binary image data set, and I compute mapper graphs for each type of image. And I create a pairwise distance matrix using the optimized mapper loss that I'm getting from my workflow. And we use multi-dimension scaling to visualize how like if this loss can cluster the close like nearby images together or not. And if you look at the picture on the right, you see that there are certain categories, for example apples and fork, which generate very different mappers. They cluster quite well together, but there are some classes, for example sea snakes and cup. These ones are not classifying very well. So we obviously have some the scope of progress here. We can look at how we generate mapper and improve that and work on that. uh, to summarize my work, so this is first available method to my knowledge which computes a bound for the interleaving distance for mappers. And we to do that, we first express mapper graphs as graphs, and these maps between mappers as matrices. And we optimize the loss which upper bounds these in the interleaving distance using the integer linear programming approach. And the initial experiments that I have run shows promising results, and of course we can run more experiments and figure out what's going on. So for future, I want to run this experiment on, first of all, a larger data set to see if this holds up and improve the efficiency of the computation. And also, as we have seen in classification, there are some cases the loss does not differentiate different classes very well. This is mainly due to how the mapper is constructed, because some of the images have different orientation, and the way I'm constructing mapper, it's highly dependent on the parameters I'm choosing. So this opens an avenue for checking if I can guide better parameter selection using my process. And of course, I would want to integrate my workflow into some machine learning pipeline for better classification and other tasks. So thank you so much. These are the collaborators I have been working with. You probably have seen them in Elena's slide too. And this is my research group where Elena was also there. And you can find my preprint. We have submitted it to archive, and we are in the process of submitting it somewhere. So thank you.
All right, let's smash that reaction button. Thank the speaker.